All right, everybody.
Because you don't do that.
So we're gonna kind of pick up where we had left off last time. So we've been going through talking about like this idea of simplifying trig expressions, right? And the tools we have for doing that is like one of two categories. You have your algebra tools, and then you have your identity tools, right? Last time we kind of went over some of those algebra tools, which involve things such as, but not limited to, like foiling, factoring, reducing fractions, making common denominators, and combining like terms and that sort of stuff. And then your identity bucket, I gave you guys an identity sheet. There's more on top of the file cabinet. If anybody didn't get one, you're welcome to grab one at your leisure. We're going to kind of continue working through some examples of doing this. Simplification process, yes? While we're going through and doing these examples, you guys should have your identity sheet out so you can follow along. Okay. All right. And here we go. Everybody ready?
Yeah.
All right. So we're looking here at notes 2 in the OneNote. This example says secant x minus 1 times secant x plus 1 all over sine squared x. So again, the typical order that you want to approach these problems is we start by looking for any algebra things to do. If you look at this, there's probably an obvious algebra thing to do at the start. Does anybody see something to do? Alex?
Would you like multiply the top of the negative one?
Yeah, so this, let's start by foiling this out, right? That looks like a FOIL problem. It's probably a good first instinct. Everybody okay with that plan? So when I multiply the first together, what's secant x times secant x? Okay, secant squared x. And then, oh, actually, before we even start foiling this out, what multiplication pattern is this? Right, that's just like an a minus b times an a plus b. That's a difference of two squares. That'll save us a little bit of time having to FOIL it, right? So it's a minus b times a plus b. FOIL out 2 every single time. A squared minus b squared. Everybody okay with what we've done so far? You say no?
No, I said yeah.
Okay. We're okay? All right. So let's continue on. Do we see any other algebra things to do? Nothing that strikes me as a good idea, right? You could try to factor the numerator back out, but then you're just right back where you started. could split the fraction into 2, but that's probably a bad idea because now you have 2 fractions instead of 1. That's less simple than before. So it's probably identity time. So if I look at the stuff I have going on here, what section of my identity sheet seems to be the one that I would want to be looking at?
The sheet that he uses.
I notice that I have a 1, an addition and subtraction. I am probably going to start by looking at my Pythagoreans because I have things that are squared and I have a 1 rattling around in there. That's usually a pretty good place to start. So if I look at my Pythagorean identities there in the middle, which one seems like the relevant one for us? P3 is a great option for us. What does P3 say? Secant squared x is equal to tan squared x plus 1. Now, in a way, this feels like not a great move because you're taking one thing and turning it into 2. But what do you notice is going to happen now that we've done that? Isaac? Yeah, so what cancels out?
Sin squared, like the SEC.
Well, we're over here, right? Because we did the identity. So there's no secant squared anymore. Nope. Yeah, I have a plus 1 and a minus 1, right? Everybody's okay there? So that's like an algebra thing. So notice that I am now quite a bit simpler than when I started, right? I'm down to like a single fraction rather than like some combination that I had before. There's no addition subtraction left. That's great. Can we do any better?
Yes.
Maybe, right? Maybe. So at this point, there's nothing algebraic to do because it's just like, it's one fraction, it can't reduce because there's nothing in common with the numerator and denominator to reduce.
Not even the x's.
Well, like, that's like, the x is part of the thing.
It's a part of the thing, yeah.
Like tan's like the operation.
Yeah, no, it makes sense. I was just curious.
Yeah, it'd be like saying, oh, I can have square root x and then cube root x and just like cancel out the x's and write this as square root over. Like that's crazy talk, right?
Yeah, it makes sense.
Okay, that's kind of the same way place we're living. So just to give you an idea, Ian.
Since tan and sin are both squared, could you square it?
Well, let me ask you this. If I have like 4 over 9, is that equal to 2/3?
No.
Then we cannot square root the top and bottom because it changes inherently the value of the fraction.
Okay.
Like not a crazy idea, but like definitely no.
Okay.
If you have an equation, you can square root both sides. That's okay. If we have an expression, you can't like just square root things or square things willy-nilly. You have to make sure the integrity, like the value of the thing doesn't
like,
change.
let's say if it says like equal to like,
If this was equal to 1,
yeah,
then you could square root both sides, for sure. But this is an expression, right? There's no equal sign at the start of the problem. So doing things to both sides is like off the table. So I think it's identity time. Now, in general, where I don't see like an obvious Pythagorean identity that I'd want to use, because there's no squareds or ones or anything, probably what I would try to do, and in general, if I'm not sure what to do, is I would try to rewrite everything in terms of sines and cosines. So sine squared I'm not going to touch because it's already sines. Tangent now, or I'm sorry, tangent squared, I'm going to look through my identity sheet and see if there's a identity that's going to turn tangent into just sines and cosines.
Q1 tan theta equals sine theta over cos theta.
Great. So Mark says if I look at Q1, that says that tan theta is equal to sine theta over cosine theta. Perfect. But I have tan squared. Can I still use that? Yeah. Okay. How does it work if I have tan squared instead of tan? You're right. Yeah, or just like sine squared over cosine squared. Is everybody okay with how I'm kind of denoting this on the board, where I'm writing the rule and highlighting like what's changing, highlight the reason I changed it, and then what the new thing is? Hopefully that makes it easy if you're going back to look at what we did and try to follow along. I'm trying real hard to invent ways to make it easy to follow when you go back and look again. Is everybody okay? Now, this seems like, again, we made it a little bit worse, right? Because now I have like a fraction inside of a fraction, which feels like kind of a nightmare. But if I look at this closely, I do have a like term in the fraction, right? What's a like in the fraction? The sine squareds, right? So what I'm going to do is I'm going to think about this like as my big fraction that contains two little fractions. The little fraction on top is sine squared over cosine squared. The little fraction on bottom is sine squared over 1. Notice that the sine squared is in the same location of the little fractions. It's in the numerator of the little fraction on top and the little fraction on bottom. Does everybody see that? What does that mean? It means I can reduce. Yeah, so those two sine squareds can reduce because it's the numerator of the little fraction on top with the numerator of the little fraction on bottom. If you have like a complex fraction, like a fraction stacked on top of a fraction like that, you can reduce numerator with numerator or denominator with denominator. Now, when we cross things out, when we reduce that, what do they become? Say it loud. 1. So that's like an algebra thing we just did here. So what I have is 1 over cosine squared over 1 over 1, or really just like 1 over cosine squared. Is everybody following what I've done so far? Okay. Now this is getting pretty good now. We have just one trig function left, right? The only way this gets simpler is if I can write this as not a fraction, right? I have a fraction with one trig function in it. The only way it gets better is if it's just no fraction at all. So I'm going to go to my identity sheet and see if I have an identity for 1 over cosine squared. What do I have? R5, which says that 1 over cosine is equal to secant But we have cosine squared. So what is the R5 going to allow us to do? It just means it's going to be secant squared, right? So any of those R and Q identities, you can use with whatever the exponent is, right? If I have 1 over cosine Q, that's fine. Just make secant Q, right? If I have tangent to the 5th x, then it's just going to make sine to the 5th x over cosine to the 5th x, right? I could just use all the R and Q identities with whatever the exponent is. Does that feel okay with everybody?
Yeah.
Oops. Let's move on to the next example. All right. So here we have cosine x over 1 minus sine x minus sine x over cosine x. Now, typically, the first thing we want to do is look for an algebra thing, right? What algebra thing could I do here? You cannot cross multiply as a solving technique. There's no equal sign to do cross multiplication. So that's not an available thing to do. In fact, it's not on our algebra list ever. You can multiply fractions straight across. Cross multiplication is a solving technique. You need an equal sign in between your two fractions to use that. What do you do if you have two fractions and you're subtracting them? Mark? Yeah, you'd want to make a least common denominator, and that's what we're going to do here. I think that's the best first move. What would the least common denominator be between these two fractions? Great, 1 minus sine x times cosine x. Because 1 minus sine x and cosine x are relatively prime. They share no factors in common. Just like if you had 1/3 plus 1/2, the common denominator is just going to be 2 times 3 because they're relatively prime, 2 and 3. They share no factors in common. Take a look at what I've written there. Are we okay with what I've done?
Yeah.
Does that all make sense?
Wait, why didn't you do cosine x on the other side?
Because
I
the
understand.
other fraction already has a cosine x in its denominator.
Yeah.
Okay. What do you want to do next? Ooh, is that okay to do? So let's think about it this way. What if I had like 4 minus 3 over 3? What you're talking about is being able to do that, right? So that would be what, like 3 or something left, like 4 minus 1 over 1. But 4 minus 3 is just 1. Is 1/3 equal to 3? No, so it definitely can't reduce that way. Is that okay? And the reason you can't is that subtraction symbol right there. If you're able to take 1 minus sign off of this piece also, yes, you could do, where everything gets a 1 minus sign taken off of it. But we can't do that in this case. This is like, you know how you guys are suggesting all of these things to do, and I'm like, ooh, can we do that? These are all algebra things that you're suggesting, right? Remember it yesterday or the day before when we started this, and I talked about how this was like, taught me more about algebra than anything I actually learned in algebra? Because what you're doing right now is you're sorting out like, oh, can I do that? No, you can't do that. Oh, that's not a real algebra thing you can do. You're really forcing yourself to come to grips with like, what can I do and what can't I do algebraically. You know what I'm saying? Like, it's such a nice like capstone task where it's like, oh, I've been doing this for a long time and getting things wrong. I'm seeing now for the first time, and it's really sinking in that like I just can't reduce that way. Like, that's just not a thing that's okay to do. And like I'm starting to see now the difference of like when I can reduce like that, when I can't, like how important where the pluses and minuses are in being able to reduce like that. You know what I'm saying, guys? Okay. Other ideas?
Use subtraction.
What do you mean by use
Like-
subtraction?
Subtract.
Well, I see something algebraically more we should be able to do here. It's in the numerator. Ian.
Actually, never mind.
Go ahead, give it a shot. Take a
Mul-
risk.
Multiply the sine x and the 1 minus sine x.
Yeah, that's exactly what we should do. We'll just distribute that sine x through. Right? That looks like something we can do, right? So the cosine squared doesn't change. Negative sine x times 1 is still just negative sine x. And negative sine x times negative sine x is positive sine squared x. Mary. So you absolutely could. I would not. And let me explain why. Okay? Because that's a great question. Mary asked, should we distribute the denominator out also? And the answer is you can, but you shouldn't. Again, the point of what we're doing is hopefully getting down to like a single thing, right? The only way that stuff is getting out of the denominator is if I reduce it. And for me to be able to reduce the fraction, the denominator has to be in a factored form anyway, right? So I would not multiply the denominator out in almost any circumstance unless, like, the denominator started as something I could multiply. Or there's like some addition subtraction where if I multiply the pieces together, maybe some stuff could combine. But here, I don't think it's going to accomplish anything. We can do it. It's not wrong to do it. But it's not getting us closer to a place where we can, like, reduce something. Does that make sense? Kind of? Okay. You'll see in a minute. Yeah, Ian.
So, so in the numerator, there's a cosine squared and a sine squared. So could you add those together using?
Absolutely. And that's where I would go next. So if you look at your identity sheet, you look at P1, it says sine squared plus cosine squared is equal to 1. And I remember from algebra that I can add things in any order. So even though sine squared and cosine squared aren't written right next to each other, they're both positive, and they're all being added, the three things up here. So we can do that. I'll stand back here and let you guys soak in what just happened. Because again, it takes a minute to like see it through. And what we're doing right now, this is not an easy task, right? Especially at the beginning where you don't have like a lot of intuition about like what to do. What are good things to do? What are bad things to do? What's like algebra I can do and what's algebra I can't do? That's part of why we're kind of like going through and doing this together as a group so we can kind of build some of that intuition that we're lacking. Yes.
Just gonna do the next one.
Yeah, go ahead.
Can you not just like times like both like 1 minus sine x on the top and the bottom by each other and then cancel them out?
So now we can reduce the 1 minus sine x's. Yes, so that is what you'd want to do, right? So if I think about the top as a 1 minus sine x, that's the only thing now in the top, right? So now we can do the reducing. I'm going to just scroll back and point out the difference being we had this other thing in the numerator at the start when Alex suggested, or no, was it you, Alex, you had suggested to do the reducing. This was getting in our way from being able to do the reducing. We had this extra thing in the top that didn't have a 1 minus sine x. But at this point, the only thing in the top is a 1 minus sine x. Now we're free to reduce it. Great choice. So that's going to just leave us with 1 over cosine x. Boy, that's a good deal, right?
Yeah.
Can we do any better than that? What's better than a fraction? Not a fraction, right? Do we have an identity that can transform that guy into not a fraction? R5 again, our friend from before. Exactly right. Hannah.
Are these identities like something that we have to pay for? Should we put them on?
I will give you the handout with the test. So not something you need to memorize.
Would we have just like this handout on the test?
It'd be like the back page.
Okay.
Yeah. For sure. How do you guys feel on this one?
Good.
It's okay? All right. So the previous 3 examples were all ones where the first step really needs to be an algebra step, right? That's not always the case. Let's do some examples where maybe the first steps are identity steps and then we do algebra to just kind of build up an intuition as to like when you might want to do one versus the other. Because there is no like set rule for like must be done this way. And there's no style points when doing this for like, oh, I did it in 3 steps versus the person that I did it in 6. Okay, correct is correct on a quiz or a test. You've done legal algebra and you've used the identities properly, and it takes you 12 steps, but you end up with the correct answer. Full marks. If the next person or the person next to you did the same, got the same answer, doing the same legal or doing different legal algebra and using different identities properly, they get full marks. It's not a speed contest, although at some point we'd like to get these things done as quickly as possible. We don't want to spend like taking the scenic route, but if that's the only route that presents itself to you and it works, you should take it rather than sitting there staring at the signpost going, this seems like a long way. Or sometimes you're not even sure how long it's going to take by looking at the problem. You're just like, okay, I'm just going to kind of keep going until I feel like I'm done. That's okay. Especially for the beginning, right? Like, everybody ready to do the next ones?
Yeah.
So if I look at this one, is there any algebra thing I could possibly do? Tangent x times cosine x.
No.
No, man, there's nothing, like, they're not like terms, it's just multiplication between them, there's no algebra to do here. Should definitely start with an identity. Any ideas as to what identity I want to do? I heard somebody whisper Q1, that is exactly what I would do. My plan would be to try to rewrite this in terms of sines and cosines. Now, cosine is already a cosine, so I don't have to worry about that. So I'm trying to rewrite tangent as sines and cosines. Q1 is my go-to there. Oops. And I'm going to rewrite cosine x as a fraction, since if I'm multiplying two fractions together, probably makes sense to write the second one as a fraction, so it's easy to tell. Is everybody happy with what happened here? What can I do next? Yeah, I can reduce out the cosines. Bloop, bloop. Now, again, when we cross these out, they become ones. So we're just left with sine x, and guess what, guys? That's it. That's it. Sometimes they're easy, right? They don't all have to be hard or long. Sometimes it's just as simple as it is. Everybody's cool? Let's keep it moving then. Cotangent u times sine u. Does this look very much in setup like the previous problem? Should, that's the point. Alex?
Can you do Q2 and change the COT to cosine over sine?
Perfect, yes. Exactly what we want to do. And again, I'm going to write the sine u as sine u over 1. Yes. Go ahead, Lucas. Hi.
Luco is here.
He is here.
Okay.
He came in tardy first.
Okay,
Period.
thank you.
You're welcome. What happens next? Yeah, we just reduce the signs out. Yep. They become ones. All that's left is cosine u in the numerator, so we just have cosine u and we're done. Okay. This feels manageable so far, not so bad. All right, let's look at our we have two more examples. Second to last example. I have 1 plus tan squared y over cosecant y. So obviously, again, any algebra thing to do here? Not really. There's no like terms to combine. There's no factoring to do. There's no foiling to do. There's no reducing to do. It's already a single fraction. It's identity time for sure. Ian, where are you looking?
Q1 turning tangent into secant over cosecant.
So you could do that. I would not. I think there's a better identity option available to us. Because unless I have like no other choice, I probably don't want to turn get myself a fraction inside of a fraction, especially if there's also addition still going on in there. It's one thing if it's like single fraction over single fraction, nothing else. Isaac.
P3.
Yeah, what about P3? So when I see the 1 pluses or 1 minuses and then something squared, I want to look at the Pythagoreans. Those guys are great ones because they often take two things and turn it into one, which is express route to making things simpler. So P3 does say that tan squared plus 1 is equal to secant squared. Does it matter that it's in a different order? No, because remember, we can add things in any order we want, right? That property is called the commutative property. So addition is commutative, multiplication is commutative.
I was gonna say like for the bottom one, we did P2, but I mean, the most simpler, that doesn't matter.
Yeah, here I like a lot better, like one fraction with no addition going on than taking and making more addition, right? So you could do that, I would not. Yeah.
Couldn't you, I wouldn't say like use Q1, but like use the logic behind Q1 to make it just tan squared because it's secant over cosecant?
Yeah, so if you look at Q1, there's two versions of that formula, right? The first version is that tangent equals sine over cosine. The second version is that tangent is equal to secant over cosecant. That's what we have here. Is everybody okay with what we did there? Are we going to be able to do any better than tangent squared? No, man, that's down to a single thing. Like, feel pretty good. That ain't bad. All right, let's look at. Oh, yes. Sure, go ahead. Not more than a sip, though. Okay, if you come back and you jump up and down, I hear sloshing, we got problems, okay? Everybody needs a joke every once in a while, right?
Yeah.
All right, last example here. So again, if we try to do an algebra thing here at the start, we have a single fraction, so that's good. Really, the only thing I'd be looking to do is to see if there's any reducing to do. Can't do that with addition going on in the numerator. Or combine like terms. But if I look in the numerator, there's no like term there. So I think this is squarely identity first off. Luco, do you see what to do? Yeah. What did you notice?
Sine squared, cosine squared.
Yeah, so as soon as we see things that are squared in addition and subtraction, that's the way to go. And remember that sine squared plus cosine squared is equal to 1. That is going to be your very good friend. We'll use that guy a lot. It's a really good one. Yeah, that's a 2. It's just a sloppy 2.
It's like a 7.
No, it's fair. It's a fair thing to ask. You know, I get it. I acknowledge that I have less than spectacular penmanship. I try, but like, sometimes it just doesn't quite get there. Yeah.
Then you use P3, correct?
Yeah, let's do it. That was supposed to be a 3. That looked more like a bracket. Oh, Mary. I always, like, I've had, like, excellent vision my entire life. Like I am.
Yeah.
When I was a young man, I had could read the bottom row on the eye chart. Like had 25 vision or whatever.
I used to have 20.
Now I don't think it's quite as sharp, but I still think at least with one eye I have better than 20/20 still.
Yeah.
So I just it's never it's one of those things I don't even think about how easy it is to see things.
Yeah, I forget that people can actually see things.
Yeah.
I have glasses since I was 5.
You've had glasses since you're 5. That's a rough
See,
one.
I have 20/20 vision, but I'm
Oh,
not
think
blind.
my vision.
I like the new flower drawing
I have
on the desk.
No. I just think nobody else.
I literally was just talking to Lucas about it. I broke my glasses like a month ago. I just can't see. And it takes 2 months to get clean. It's
Way better. And I'm
That's rough.
Yeah.
Yeah, no, it's hilarious.
I moved down on anything on the board.
Well, it's a good thing that everything is backed up onto the tablet.
Yeah, I know. That's all it is.
All right, we're almost there on this one. We're at secant squared u over secant u. Yeah, we just
Take out CK.
it's just like x squared over x, right?
And then that goes away.
Yeah.
Oh.
But how do you take it out?
Well, it's just like x squared over x, right? How does x squared over x reduce? Just becomes x, right? What does secant squared over secant reduce to? Just secant. It's the same idea. And again, down to one thing. Tough to beat that. What do you guys say? Was great.
I like it.
All right. So I have 2 handouts for us to work on. These will be part of Sunday's problem set. The first one is just practicing foiling and factoring. Some of these include trig expressions when you're doing it. And then I have another handout that is doing just what we got done practicing here.
I'm not No, I do have cyberpunk. The world is just against me.
It's a grand conspiracy. We have our daily meetings at 3:46 a.m. Figuring out what we're gonna do each day.
They're out to get me.
Yeah, no, it's funny. I have more perfect. I don't want to make myself. Then I cut.
I don't know. Membership needed to buy.
It comes to sign. It comes to sign.
Mr. Little.
Oh, I do that, yeah.
Mr. Little.
Oh, yeah.
Ask us what color is it?
I got like $4 tonight.
I'm gonna play all the CT.
All right. So what do we got? We got
30 minutes.
35 or so minutes left here in class, right?
Punch it out.
It's a busy week for everybody. I've heard everybody complaining about tests and quizzes and all this stuff going on, and sports season's winding up or winding down or ramping up.
Yeah.
Plays and everything going on. Take this time in class. It's a big chunk of time. Focus in, knock some stuff out, do yourself a favor, get something done. Don't waste the time. So put away our phones, call back your clans, put a piece on there. You know, like your other homeworks I know are important too, but let's do this right now, where I can help you and if you got questions. But let's lock in and try to make some progress here, okay?